We're looking at number 63 now on page 561 from chapter 10. What we are looking for here is a mean value. It's talking about nutritional content of prepackaged foods. So I'm going to say that I'm dealing with the average nutritional value. In this case, the average calorie content. So I'm going to say mu is the true mean calorie content for a certain type of frozen dinner. So that's going to be what I have there. Okay, then the next thing I'm going to do is I'm going to have to do my null hypothesis. So your null hypothesis in this case should be that your mean, or mu, is equal to looks like 240 is the number they're giving you in part B of this problem, so we'll go ahead and write our null hypothesis this way. And then our alternate hypothesis is going to be that it differs from 240, because in part B it just asks for differ. So differ, I'm just going to need a not equal to there. Okay, now I'm going to need to go ahead and check my assumptions. My assumptions always need a random sample. So it is given that I have a random sample of this type of frozen dinner. We didn't just take them all out of the same lot or all out of the same grocery shelf. We have a random sample of this type of frozen dinner. And then also I need to know something about the shape of the sampling distribution. Now my sample is not sufficiently large, so I cannot invoke central limit theorem. My sample size is only 12, so I can't use central limit theorem to say the sampling distribution is approximately normal. I also cannot, in this case, know any information about the population distribution itself. So I have to use the shape of the sample distribution. So I'm going to say that since the box plot for my sample distribution is symmetric with no outliers, it is reasonable to assume that this data came from a normally distributed population, since sigma is unknown. T distribution would be appropriate. Okay. I could have talked about the normal probability plot as well, because the normal probability plot showed a strong linear relationship, but it's unnecessary to use both of them. So you can, if you wanted to talk about the normal probability plot as well, or if you had a question that only gave you a normal probability plot, a strong linear relationship in the normal probability plot also suggests that the sample data is approximately normal and probably came, and it's reasonable to think it came from a population. Please note that you have the sample distribution, and you're making it clear that you're using your sample distribution to assume that the population distribution is approximately normal. It's very important to make it clear that you're not making an argument based on the sample data, but you're using the sample data to talk about the likelihood of the population data being normal. Questions so far? Now, what we're going to do is we're going to do a one sample t-test for population means. When you name the test, always tell what you're testing. In this case, one sample. A t-test is what statistic you're using, and population mean is what we're testing for. So there's several things I need. I need a sample size, in this case 12. I need my degrees of freedom, which is n-1, so it's 11. I need a x bar, or my sample mean, and I also need my sample standard deviation. Now this is not given to me in the problem, so what I'm going to have to do is I'm going to have to reach for my calculator and put this data in. So I'm going to go to Stat Edit. If I already have data in L1, which I do, I'm going to clear it out, and then I'm going to type in my new data into L1. So 255, 244, 239, and so on. be sure to double check your data. A typo can make a very difficult to understand error in your work. And also make sure you have 12 of them. Looks like I've got a 26 instead of a 226. That's an issue. So now that that's fixed, I'm ready to do, and I've double checked to make sure my last piece of data is data 12, that I didn't skip one. I can do stat, calculate 1 bar stats, just do it on L1, and the values I'm looking for x bar are 244.33, and for the sample standard deviation, it's going to be 12.383. Okay. Once you have that, it's guess it's time to go ahead and state my alpha. So my alpha in this case is in this case, it does not appear that the problem gave us an alpha level, so a good alpha level to use is 0.05. If it doesn't give you one, that'll work as well as anything. And now once you've defined your alpha, it's time to go ahead and start looking for a sample statistic. Your p-value. Those are all my sample statistics, including my alpha level. Now I can look for a p-value. So I'm looking for the probability that x bar is greater than, looking for the probability that my x bar is not equal to that sample mean of 2.443, or that it's significantly different from that. So to do that, my test statistic in this case is a t, because it's a t-test. So it's 244.33 is my statistic minus my parameter. In this case, it's my hypothesized value of 240. That's my hypothesized parameter, my hypothesized mean. And then my standard deviation is my sample standard deviation divided by the square root of my sample size. So the square root of my sample size in this case is 12. That's going to give me my value there. So let's go back to the calculator. And we need to type that thing in, 244.33 minus 240. That's your numerator. My denominator is 12.383 divided by the square root of 12. That's your typical value you're off by. So we're typically off by about 3.5. So in this case, being off by 4.3, when I'm typically off by 3.57, is going to be a t-score of about 1. So that basically is going to equal the probability that, get all that on one line, the probability that t is greater than 1.211. Of course, this is with 11 degrees of freedom. So to get the appropriate p-value, I'm now going to go to second distribution. I have a test statistic. I'm looking for a value, so I'm going to do TCDF. I'm going to start at my 2.11, which is my previous answer on my calculator. I'm going to go to a really big number. That'll work. My degrees of freedom is 11. I'm going to paste it in, and that's going to give me a value. Now this value it gives me so far, you notice, is just the probability I'm greater than. So I'm going to sketch this distribution, hopefully to show you where this is coming from. If I am looking at this distribution, I'll be looking there. So on the end of the t-distribution, I'll be looking right there at the 1 and looking there, but it's also just as bad to be off on the other end, which is that. So I'm basically going to have to double my p-value. You have to realize that you're equally likely, it's equally bad if you're looking at a not equal to or a two-tailed test to be, basically 4 below what you expected of 240. So a t-score of negative 1.21. So that's why I have this probability on the left side here of 0.1256. And then for your final answer, what you're going to have to do is basically you can double the p-value your calculator gave you. So I can just take that answer, multiply it by 2. Oop. Let's try again. Take my answer and multiply it by 2, and that's going to give me a p-value of 0.25. So my actual p-value, that would be the true p-value that is greater than, but if I was looking for the p-value that it was not equal to this, that's going to double it to that number we just got with our calculator of 2511. So since my p-value is that high, I'm going to say since my p-value of 0.2511 is not less than my alpha of 0.05, I'm going to fail to reject my null hypothesis. Now, if you fail to reject your null hypothesis, that means there is no statistically significant evidence that my alternate hypothesis is true. So in the context of this problem, it's no statistically significant evidence that the true mean calorie content of this particular frozen dinner differs from 240 calories. And the reason I say differ as opposed to greater than or less than is because I was testing for not equal to ever since my alternate hypothesis. It's a two-tailed test. So basically the catch is on the two-tailed test, once you get the p-value from your calculator, remember to double it to take care of the fact you've got two separate tails.